Okay, so moving on, what is a voltage divider? Well, your text says a circuit consisting of a series string of resistors connected to a voltage source acts as a voltage divider. So if we look at the diagram below, really what it looks like is a series circuit. We have two little funny grounds on here, but it's basically a series circuit. We've got a source, we've got two resistors. Okay, although there can be any number of resistors, there are two voltage drops across the resistor, one across R1 and one across R2. So we've already figured this out, okay? These voltage drops are voltage 1 and voltage 2, respectively, as indicated in the schematic. Since each resistor has the same current, the voltage drops are proportional to the resistance values. For example, if the value of R2 is twice that of R1, then the value of V2 is twice that of V1. So you see, we've got some proportionalities here that give us a hint what's going on. The total voltage drop around a single closed path divides among the series resistors in amounts directly proportional to the resistance values. Okay, so for example, if the source were 10 volts, R1 were 50 ohms, R2 were 100 ohms, then V1 is 1/3 the total voltage, or 3.33 volts, because R1 is 1/3 the total resistance of 150 ohms. Likewise, V2 is 2/3 of the source, or 6.67. So what you should start to see here as you're working with these relationships is understanding what's going on in the math, so that you start getting a seat of the pants idea of what an analysis should look like, and if your analysis really is making any sense. So we could come up with some voltage divider formulas. With a few calculations, you can develop a formula for determining how the voltages divide among series resistors. Assume a circuit with N resistors in series as shown. So in this simple circuit, we've got R1, R2, R3, and who knows how many more out to the nth resistor. So in each case, you should start to see if I've got a source, and later we're going to see that source could actually become a transformer, okay, that's tied to another source. But anyway, we have voltage drops across each one of these resistors. And we could pick up a voltage at the first node here, at the second node here, at the third node, fourth node, and out to the nth node. So if we let V sub x represent the voltage drop across any one of the resistors, and R sub x represent the number of particular resistor or combinations of resistors, by Ohm's law, you can express the voltage drop as R sub x as follows. So you can see we've got this product, V sub x is equal to I times R sub x, and we could use it to calculate the voltage drop and therefore understand this voltage divider relationship that we've got going on. The current through the circuit is equal to the source voltage divided by the total resistance, and we've already seen that. That total resistance and the total voltage source determines what the current is in a simple series circuit. In the circuit 537, the total resistance then is the sum of all of the resistors in the circuit. By substitution then, V sub s over RT for the total current in the expression for V sub x is equal to the source divided by the total resistance multiplied by the resistor of interest. So we can rearrange the terms here a little bit, and we can get V sub x is equal to R sub x, the resistor of interest, divided by the resistance total multiplied times the source voltage. This is the general expression for a voltage divider formula. Okay, so it can be restated as the voltage drop across any resistor or combination of resistors in a series circuit is equal to the ratio of that resistance value to the total resistance multiplied by the source. So in your notebook where you're keeping all of your relationships for handy dandy reference, your toolbox, you should write this relationship down, and it probably wouldn't hurt to put the definition here on the bottom as well. So let's look at an example. Determine V sub 1, the voltage across R1. Okay, so that's up here on the top. And V2, the voltage across R2 in the voltage divider. So in both cases, we are given a resistor value, 100 ohms and 56 ohms, and we have our total voltage. To determine V sub 1, use the voltage divider formula. So we're going to go back to that formula. V sub x is equal to R sub x divided by the total resistance times the total source, where x is equal to 1. Okay, the total resistance then is equal to R1 plus R2, 100 ohms plus 56 ohms, or 156 ohms. R1 is 100 ohms, that's given. V source is 10 volts, that's given. Substitute these values into the voltage divider formula. So now we can say, okay, V sub x is R1, R total, and we have V sub s. So R1 is 100 ohms, R total is 156 ohms, V sub s is 10 volts, so we get a voltage drop of 6.41 volts. So at that point, R1, we could pick off 6.41 volts to drive some other part of a circuit. There are two ways to find the value of V2. We can either use Kirchhoff's voltage law, or we could again apply the voltage divider formula. So if you use Kirchhoff's voltage law, V sub s is equal to V1 plus V2, substitute the values for V sub s and V sub I, we very simply end up with V2 is equal to the source. We subtract what we just found for V sub 1, and we get 3.59 volts. To determine V2, using the voltage divider formula, where x becomes 2, now we have 56 for R2, 156 times 10, and we get the same 3.59 volts. So you can see we're starting to develop that you can get the answer using a number of relationships that we've learned. Okay, so now let's look at another one. We've got 3 resistors in series. Calculate the voltage drop across each resistor in the voltage divider. So in this case, 3 resistors, 3 unknown voltage drops, 3 resistor values given, and a source. So if we look at the circuit for a moment and consider the following. First, the total resistance is 1,000 ohms, so we know R sub T. 10% of the voltage is across R1. Okay, why do we know that? Well, 1,000 ohms here, 100 ohms here, 1,000 ohms total, 10%. Because 10% of the total resistance, 100 ohms, is 10% of 1,000. Likewise, 22% of the total voltage is dropped across R2. So, because 22% of the total resistance, 220 ohms, is 22% of 1,000. And finally, using the same logic, R3 drops 68% of the total voltage because 680 ohms is 68%. Okay, this just works out. This works out because we've got 1,000 ohms total here. I mean, the numbers work out cleanly for us. But the analogy there is good. We can start to see how the math bears out, and we could come up with some simple explanations and some simple solutions. Because the convenient values of this problem, it's easy to figure out the voltages mentally. So V1 would have to be 0.1 or 1/10 of 10 volts, 1 volt. V2, 22 hundredths of 10 volts, 2.2 volts. And V3, 68 hundredths of 10 volts, or 6.8 volts. So, such is usually, though, not the case. But sometimes a little thinking will produce a result more efficiently and eliminate some calculating. So, you'd have to have some intuitive insight to look at this and come up with it. But store this away as something you might be able to use later. This is also a good way to estimate what your results should be so that you'll recognize an unreasonable answer as a result of a calculation error. Okay, so this goes back to putting a bunch of numbers in your calculator. You come up with a value. You don't know whether you're going to trust it or not. You think it's good. You give the answer, and it's wrong because you didn't understand the problem. And you trusted that the calculator must be right because it gave you that number. So it should cause you to start thinking about, erring here and staying on the side of caution. Although you've already reasoned through this problem, the calculations will verify your results. So, take a look at this. You can see we've got our voltage divider formula. In each case, running it through your calculator, you'll end up with 1 volt, 2.2, and 6.8 volts. Notice that the sum of the voltage drops is equal to the source voltage in accordance with Kirchhoff's voltage law. This check is a good way to verify your results. Okay, the next one here, they ask you to determine the voltages between the following points in the voltage divider. So now we've got pick-off points here. We've got point A, B, C, and D, where we're picking off voltages from the source as they've been divided or the voltage drops occurring. Okay, so if we first determine the total resistance, we come up with 12.5 k ohms. And if we apply the voltage divider formula to each of the required voltages, now we're going to use a double subscript: voltage A to B, voltage A to C, voltage B to C, voltage B to D, voltage C to D. So in each case, you'll notice in the numerator, we've done something a little different. Okay, in the numerator here, R1 makes sense because that's A to B. In A to C, though, we've got 2 resistors. So we have to add R1 and R2. Voltage B to C, we've got 1 resistor, R2. In voltage B to D, again, we've got 2 resistors, R2 and R3. And finally, C to D, our last resistor, R3, is just R3. So you have to look and determine how many resistors are in play for you to determine the correct voltage divider. So in A to B, we end up with 2 volts. In A to C, we end up with 18.4 volts. In VBC, B to C, we've got 16.4 volts. B to D, 23 volts. And C to D, 6.6 volts. So if you connect this voltage divider, you can verify each of the calculating voltages by connecting a voltmeter between the appropriate points in each case. So hopefully in your lab, you'll be doing something like this. If not, hey, pull out some resistors, set up your proto board, and try it for yourself. Set your power supply to 25 volts and verify that something like this does in fact work. So when we come back, we'll take a look at the voltage divider formula and the application of something called a potentiometer as an adjustable voltage divider.